Okay, we'll go ahead and get started. I've started the recording, and yeah, so I'm back in Missouri. It was great seeing most of y'all, and grateful that a few of you were able to stop by and chat with me either during office hours or before or after class. And just always helps me, and I think it helps you a lot too, to have some of those conversations with your professors. I know this is late in your undergrad academic career, so maybe this advice is getting too late, but there has been some really positive research around how students that have contact with their professors outside of normal lecture hours, that could be, participating in office hours or, doing some undergraduate research, that type of thing, that they end up having much better careers in the long run. So some longitudinal studies that have shown that. So particularly if you go to grad school, even if you don't do a thesis option, I really encourage you to have some time with your professors and all that type of thing. So blah blah blah. Looks like a lot of people are joining online. As a reminder, we do not have class on Friday, so that's I guess encompassing a lot of religious holidays. So however you celebrate, if you do or not, gives you a little bit of extra time to reset. And so our assignments should be due, I think, tonight, but as I said, I give you a little bit of flexibility on that. Just thinking that it's great for y'all to have an ability to just take this time off. I do have another assignment that is on this error control coding topics, and I will probably be releasing that over the next couple of days. But I'm gonna give a due date such that you have some flexibility and all that. So let's go ahead and get started now with our lecture, and let's get okay. So hopefully you're seeing my screen, and also note that I have uploaded last week's lectures. Again, there was a little bit of a quirk on a major quirk, I guess, on the Tuesday lecture. It only got about 13 or 14 minutes worth before the meeting closed itself, but I was able to get some recording of that. And I only looked at a few minutes of it, a few seconds of it, but it looks like it did capture that first part of the lecture. And then Friday's lecture is up there also. So today we're going to continue talking about error control coding, but now last Friday we talked about linear block codes, and now we're going to talk about convolutional codes. And we'll look at their generation and then how we decode them. You may have, when you either read the textbook or you looked at some of the MATLAB documentations on some of the demodulators that we've looked at and stuff, you may have seen some mention of hard or soft decisions. So we'll talk about those a little bit today. We'll mostly still focus on hard decisions, but it's good to to know that the soft decision concepts actually exist, and typically more superior in terms of performance than hard decision. And then we'll talk about the Viterbi decoder, one of the most important algorithms. The FFT is probably the most important algorithm in communication systems, but the Viterbi certainly ranks up there. So, all right. So another class of error control coding distinct from block codes, right? Typically, in convolutional codes, we only send the parity bits. And that means that it's not systematic. So recall that systematic codes, that block codes are typically systematic, and that the message word appears intact in the code word, right? And so in linear block codes, we have a message word plus some parity bits associated with that message, right? And so the concatenation of those form the overall code word. In convolutional codes, that's not normally the case. And so we're only sending the parity bits. And so we have to take those parity bits and extract out the message word. Okay, so the information in the message bits are now spread out through several of these parity bits that we're sending. Because of that, it's well suited for burst errors, right? While block codes, linear block codes, excel at errors due to random Gaussian noise, right? So there was a little mention of kind of an assumption we made in linear block codes, is that the error probability from one bit to the next is independent of each other, right? So that P sub E for each of those bits, that binary symmetric channel, there's equal likelihood of those bits flipping from 0 to 1 or 1 to 0. And so that is, meaningful in terms of Gaussian noise, right? And but what about when you have maybe a whole number of symbols or bits that are wiped out, either by some jamming interference, or maybe you drive through a shadow, electromagnetic shadow from the antenna. You got a building in between you and the base station, let's say in a mobile communication system, or you go through a fade. We mentioned this, and I haven't gone into a lot of detail, but when you have reflections of the electromagnetic signal wave as it's traveling from the transmitter to the receiver, and so you end up with multiple paths that have a little bit different lengths, and therefore when all of those different waves or rays, sometimes we model them as rays, when they reach the antenna and they induce current into that antenna, but they induce it at different phases, and so sometimes you have some cancellation, right? So that can now cause some errors over a longer period of time than just a single symbol or bit. So we call those burst errors. And so convolutional codes are particularly well adept at dealing with those, right? So these codes have memory, right? This is a big thing about that. Maybe that makes a good test question, that these things have memory. And that means that allows us to spread the impact of a single bit over several output parity bits. So conversely, a given parity bit includes the effects of current and several past input bits, right? So there's a smearing or spreading of these effects, and that's really kind of maybe intuitively how we adapt these things towards dealing with burst errors, right? These errors that persist over multiple bits, right? So we're spreading the impact over many instead of just maybe one or two of these parity check bits. Right? So here we describe this memory depth as the constraint length, and we'll typically call that a capital K. You'll also see maybe a capital L in some contexts, and we'll that's maybe that shows up in a Viterbi decoder or something like that, right? So what this does, though, is that it results in 2 to the K minus 1 states, right? So we have memory, and therefore we have different states that the encoder can exist in, right, depending upon the memory values. So here's a description of how we do this, right? So we're going to modulo 2 all this because we're dealing with bits, right? We're mapping some input bits into output bits. So we're going to use modulo 2 math. That means that we're still, our results are still going to be mapped to 0 and 1, right, as logical bit values, right? Remember that modulo 2, we can look at like the exclusive OR gate, logic gate as implementing the arithmetic math associated with that. So here we're going to have some input bits, this x n minus j, where j is going to run from 0 to this cap k minus 1. That's going to address this memory aspect, or the constraint length, right? And then we have this generator polynomial, and we typically have more than one. 2 is a very common number, and so we'll have maybe 2 different generator polynomials, and that results in a sequence of output bits, n, right? But that there's an output bit that results from each generator polynomial, right? So G sub I is the kth element generator polynomial for parity bit P sub I, right? So we mathematically, we describe these as polynomials that have k elements associated with them. So each P sub I represents another parity bit generated from the message. Typically, we have multiple generators. So I write this as that I goes from 0 to 1 to ... right? So, and these are normally interleaved at the output. So we'll have a bit from generator G0, and then that would be followed by a bit from generator G1. We see that down here, but it's possible to have multiple input bits, so little k greater than 1 per convolution, but it's common to process each input bit continuously. So this little k equals 1, right? So then that leaves us with the code rate formula that's basically 1 over the number of generators, right? So if we have 2 generators, then our code rate would be 1/2, right? And so then we would see, if we start at the beginning of time here, or the beginning of a sequence that we're going to convolutionally encode, then we would have the 0th output bit from generator 0. Then we would follow that with the 0th output bit from the generator 1, G sub 1. Right? And then we would follow it with the second, or number 1 output bit for generator 0, and so on, right? So this is that interleaving that we that I mentioned in the previous slide. So we'd have these bits, these n bits here, 0, 1, 2, but we're going to interleave the output with these different generators, right? Here we have 2 generators. So here's an example. we're going to have generator G0, and that's going to be modeled as 1, 1, 1, 0, 0, dot, dot, dot. Right? So we write this in shorthand as 1, 1, 1 for a capital K equals 3. Right? So that constraint length is K equals 3. And then we're going to have a second generator that's going to output a 1, 0, 1, 0, 0. And we'll use a shorthand of 1, 0, 1 for that. Now, what does that really mean? Right? So we can write this generator polynomial as, since here this, if we have a input, we are going to take the outputs from the memory of the state machine here, or the system, and we're going to take a value from each of those locations, right? So we'll have xn, which is the present value n, right? And then we're going to take the previous value and then the previous value from that, right? So and we're going to sum these up again using modulo 2 math, right? And then that's going to become the single output bit, right? So this single output bit at step n for polynomial 0 is a modulo 2 addition of the current value and the prior two memory states, right? And then P sub 1 is very similar, except we don't take the value of the first memory location. We only take the present value and the one a couple of steps behind, right? So here, let's put an impulse in as an input. So an impulse would be like 0, 0, 1, 0, 0, right? So we're going to end up with now, so we can look over here, and this is like our memory over time. So we'll start with a system that's reset to 0, and then we have 0, but then we have a 1 come into place, right? And we'll go from left to right in this convention here. So now we have a 1 that's input into our system, and then the next time step, we introduce a 0, right? But that 1 now gets stepped across and ultimately to the second memory location, the first memory location, the second one, and then it falls out, right? So if we looked at the memory registers over time, that's what this would look like for this impulse input. Okay? So now we can look at time 0, we get a 0 in, time n equals 1, we still have a 0, and now at time n equals 2. So you can start plugging these things in here into this generator, and it's helpful to reference these memory locations, right? So now at let's see, this memory time, we are going to have a 1 plus 0 plus 0, right? So that's a 1. And then in the next step of time, we're going to have a 0 plus 1 plus 0, right? Still equals to 1. And then the following time instant, we're going to have a 0, 0, and a 1, still equal to 1 in a modulo 2 sense or whatever. And so we'll have a 1 there also. And then they start to drop out. And similar, you should maybe follow through here on the P sub 1 and like plug these values in, but you're going to get a 1, 0, 1 in that case. Now what we do is we interleave the results, right? So we'll have a 0 and a 0, 0, 0, 1, 1, 1, 0, 1, 1. I think maybe one of these ones, I have to think about that. Now that I'm looking at it, I'm not sure I agree with it. But okay, so this diagram shows it maybe a little easier to think through. So again, this is a modulo 2 type of addition that's going on, and you can use this as how the memory locations evolve over time, right? So this is a present value, and then this is a memory location taking the prior value, and then this is a memory location holding the a second prior value, right? And then we see that for the P or G0 polynomial, we're generator polynomial, we're taking inputs from each of those locations, doing a modulo 2, and then making that available to the output. In the P sub 1 or G sub 1 situation, we're taking it from the present value and then that second memory location. And modulo 2, provide that to the output. And now this output, this switch here, is the permutation, right? So at each end coming in here, we're actually going to be outputting 2 values, right? So for every bit that comes in, we're outputting 2 values, one from here and one from here, right? So we have a code rate of 1/2. So our code words are going to have twice as many bits as our input words, right? So so this is all easily implemented using a shift register made out of flip-flops that are clocked at this rate n here and shifting data through. And of course, as the data gets here, it just falls off to oblivion, right? And but that shift register or these flip-flops are providing that memory state. All right, so now if we think about it, we've got some trade-offs, right? So if we have a constant power situation, maybe the easiest to think about, then a code rate of 1/2 requires twice the bandwidth, right? So we have twice as many bits coming out as we do coming in, right? So we're going to need twice the bandwidth eventually as we modulate them and then transmit them, right? And therefore, our energy per output bit is 1/2 relative to the input, right? So so as we kind of map that energy from symbols to code word bits to message bits, then there's that again a division of 2 towards that input bit. So the gain is provided by the structure of the code, right? So there's a certain structure. So as we input values in here, there's a particular legal structure that this encoder provides, right? And so that's helping us get what we call a coding gain. Okay? Now, conversely, if we have constant bandwidth in our system, right, we're kind of comparing using a convolutional code or not, maybe using a code rate of 1/2 or 1/3 or 1/4, right? So now, if we can't take that and use more bandwidth to send these higher rate code words, we could use a higher M-ARY type of modulation, right? So use Comm or QPSK or so on, right? And in this case, our distance in the constellation is reduced, or we're requiring more energy, right? To send it, right? So and again, we're relying on the structure for improvement, right? So think about this a little bit in the context of that Shannon's capacity theorem, right? Where we say that the capacity of a channel approaches the bandwidth times the log base 2 of 1 plus the signal divided by the noise power, right? Signal noise ratio. And so we talked about how Shannon proves that the that produces a limit, right? That we can't really go beyond that. We can't expect to get more capacity out of the channel than what those parameters in that equation provides. But it didn't really tell us how to do it, right? So now we're learning here these linear block codes and these convolutional codes are to approaching that limit, right? And again, it's that structure provided in the code, that redundancy that allows us to approach that. So even though we're sending more bits, therefore it takes more bandwidth. So we would think that that's kind of a negative in terms of our capacity, right? If our code word takes more bandwidth to send than our message bits, right? Or it takes more power to send or less noise to send than our message bits uncoded would, right? But we actually get an enhancement through all this structure. All right, so speaking of distance, right? So the system provides code words, as in block codes. The smallest weight non-zero code word sets the distance, and that in this case we tend to call it the free distance. It's analogous to the Hamming distance, right? So now we can model this system because it has memory. We can model it using a state diagram. And here, let's see, I've got a state of 0, 0. So our memory locations are holding 0, 0, or 0, 1, or 1, 0, or 1, 1, right? So those are the 4 different states that the system can exist in, right? So again, we have the input bit and then the 2 prior bits in time, right, that are held in the memory. So there's really 2 memory locations, right? So even though there's 3 bits that are making up this output, right, but where one of those bits is the input, and we don't need memory for that. So here, okay, recall your state diagrams from your digital logic course 229 or something like that, right? So here we have describing if we get some input bit, then what is our output, and how do we transition from state to state, right? So if we're in state 1, 1 and we get a bit of 1, we're still going to stay in state 1, 1. If we're in state 0, 1 and let's see, did I draw this right? If we get a 1, I think I have some issues there. But so this describes the evolution of a state system, right? So I'm just thinking that these input bits might be reversed, or the directions of these arrows might be reversed. So, but we're typically going to use a trellis diagram. I think we talked about a trellis diagram early in the semester, did not go in that much depth. Here, this trellis is going to be very important in decoding our codes at the receiver, right? And but it's also used to model the evolution of the code at the generator, right? So a trellis diagram is a way of describing a state machine, but instead of just looking at one instant of time, we can look at it as and see how the system evolves over these time steps, right? So if we look at this, we have the 4 different states for this k equals 3, right? So we have n minus 1 states, I think. So here we have a 0, 0 state, 0, 1, 1, 0, 1, 1. Again, these are the values of the memory in that shift register in those flip-flops, right? And so that would be equivalent to these 4 different states here, right? And now we show these transitions, right? So we have the input bit, either a 0 or a 1, right, from this state. And then we also have the output parity bits, right? So for this um, uh, system, we have where we have 2 different generator polynomials. We'll have an input bit, and that will produce 2 output bits, right? But if we start in 0, 0 and we get a 0, then we're going to stay in state 0, 0, right? But if we start in 0, 0 and we get a 1, then we're going to transition to this 0, 1 state. Now, at this point, I should say that it's kind of essential to kind of keep in your mind for any given notation that you're looking at, which direction these things are going in, right? Sometimes we will write it such that things are clocked in from left to right, and other times we're clocking them in from right to left. So just be kind of careful of that and be consistent as you're going through that, right? So, and so now we've started at maybe time step 0, and now we've evolved to time step 2, right? And then at time step 2, we could be in either of these 2 different states, depending upon the prior bit. Now, there's a little note to be made here that we usually start and end with 0, 0 to initialize and flush this trellis or state diagram, right? So we'll kind of reset the system so that our memory locations are at 0, 0, and that way there's no kind of precondition that we have to worry about that may affect how this code evolves, right? So we reset everything to 0, and then if we're sending a finite number of bits, then we'll typically go ahead and flush the trellis with zeros, so that then the next time we're ready to start back in this 0, 0. That's why you see kind of this funny shape to it, right? And but as we evolve over time, now we see that we're present, we can be present in any of these 4 states, right? Depending upon its history, right? So we can take different paths through these this trellis, right? And that's the advantage of this trellis diagram. It shows how this system is evolving over time, right? But each of these is a state transition, and we might be staying in the same state, or we might be transitioning state. Note that in this system, there's certain legal state transitions, right? And then there's state transitions that should not exist, right? So if we're in state 0, 0, there should be no direct way of getting to state 1, 0 or 1, 1, right? Though there's no way to go from here, this 0, 0, where we just have 1 input bit, right, and 1 time step, and there should be no way to get to this 1, 0 or 1, 1 state, right? And you can look at that from any of these different states. There's only certain legal transitions depending upon whether our next bit is a 0 or a 1, right? And so that's what this state diagram is, or this trellis is showing us, right? So so that's kind of how we might generate it, right? And then we're taking our inputs, or outputs, I'm sorry, from these bits here, right? So these the ones that follow this slash, right? So this is similar in the notation you saw when you studied more in Mealy type state diagrams in 229. All right, now if we generated it, we're going to want to decode it, right, at the receiver. We've got to take, we're going to get these code words, and now we got to try to estimate what the input or the message was, right? And remember that in these convolutional codes, we're only at the receiver, we're only getting the parity bits, right? Because it's not a systematic code. So we got to take those parity bits and somehow reclaim, rediscover the message bits that originally generated those, right? And we want to do that in a way that's, of course, robust to some errors, right? That's the whole reason we're doing this error control coding, whether it's linear block codes or convolutional codes, right? So in decoding at the receiver, we want to estimate the original message sequence based upon the receive bits and the knowledge of the code structure, right? So we've got to understand, we've got to have this trellis in our system, right? We've got to have this knowledge of this at the receiver. We got to know how the thing was generated, because what we're going to rely on is this knowledge of particular legal transitions as opposed to illegal or impossible transitions, right? So now when we're dealing with this, you recall earlier I mentioned this hard versus soft decisions in the outline of the lecture, right? So hard decisions use the bit decisions from the threshold detector in the receiver, right? And so we're getting as inputs into this decoder either a 0 or a 1 for each parity bit, right? So we know that that each parity bit is either going to be a 0 or a 1. And that's what we're going to talk about in the lecture and so on, right? So, but there's also, it's also possible to use soft decisions, right? So we're going to skip the threshold stage and essentially use the integrated voltages from the output of the sampler at time t. Now, mathematically, you might be looking at, measuring this in terms of probabilities or that type of thing, right? But physically, we're kind of looking at these integrated voltages, right? Hard decisions kind of throw away a lot of that information, right? So you're quantizing it here, right? So we don't know whether that when we mapped it to a bit 1, whether that was let's say our voltage ranges from 0 to 1, right? And we're now trying to map that into logical values at 0 to 1, right? So that would be an on-off type of modulator, right? So let's just assume that for simplicity. Then when we're dealing with hard decisions and we mapped it, we thresholded it to a value, a logical value of 1, we don't know whether that voltage was 0.6 or 0.9 or 0.999 or maybe 1.001 or something like that, right? It could have just barely made it over that threshold, 5.001 or I'm sorry, 0.5001 or something like that, right? So soft decisions kind of retain that information, and assuming your algorithm can handle that, is generally superior, right? So just as a reminder, here's our correlation receiver, and we would have this thresholder out here, right? And or we'd have a match filter, right? And we'd have some of these, and we'd have a threshold device here, but we're outputting a voltage, right, at this sampling location point in time that's been convol through this or integrated through all of this, right? So, maybe it's a little bit more complicated than that in typical implementations. There might be some other stuff going on here, but in this demodulating when you're like going from a large cap M, and that type of thing. But the point is for soft decisions, you have real numbers versus a hard decision. You've already mapped it to 0 or 1. Okay, so now the Viterbi algorithm is a maximally likelihood decoder that is used in a number of different applications and communications, and actually you see it in some forms in some machine learning type applications also, right? So it's a very powerful type of decoder, and we're going to look at the one that's basically used to decode convolutional codes using hard decisions. Okay, and the way it works is we're going to calculate a branch metric for each time step of the message data. What this is it's the difference in the received values versus the expected values in the context of that trellis, right? So that trellis says that to get to a certain state at that time step, you would expect to have certain input values, right? So we're going to compare that to what we received from that threshold detector, right? And then hopefully our branch metric, well, ideally it would be 0, right? Because they would be the same. We're looking at the difference, right? So, but maybe it was supposed to be a 1-1 and we got a 0-0. So now our branch metric would be 2, right? Because we differed in both of those locations, right? Now, we also keep track of a path metric. So this is the summed values for each path through the trellis. Okay, so we perform that calculation for each possible state. Then we're going to retain the best path into each state. And we call that the survivor path. And that's done on this minimum distance, which is essentially making it a maximum likelihood decoder, right? So we're looking at the maximum probability that this is what was actually sent, right? So that we're going to see some examples of this, right? So I know that's a lot of words, and but we're gonna see how we're going to work through an example here in a couple of minutes. So but you're going to refer back to this slide, right? So this is essentially the statement of the first part of the algorithm, right? So we're going to calculate the path metrics through the trellis for each time step for all the received messages. At each of these time steps, we're going to use this EECE, or add, compare, select, to calculate that branch metric, and then select add that to the path metric, and then select the best survivor, right? So then at the end, right, now we've marched through this trellis and updated it at each of these time steps, and we have processed all of our received bits. Now we're going to trace back the path that has the minimum path metric, right? So remember, the path metric is the sum of all these individual branch metrics, and a branch metric is ideally 0. It's the difference between what we got and what we expected, right? So if we got what we expected, then there's no errors, and so that branch metric would be 0, 0, right? And so we're looking at the minimum path metric at the end. So then we look up the message bits corresponding to all the transitions that produced that path for that minimum path metric. Again, we're going to see some examples of this, right? So on that trellis, recall that we have all these message bits that would correspond to the parity bits, right? So now we trace back and look at those message bits on each of those transitions that correspond to producing this path. Then that would actually kind of give us a reverse order. So we just do a reversal on that. So technically there's a reorder of the message bits. And now we're going to note that this is fairly memory and compute intensive, right? So we've got to calculate all these things. We got to keep all these things in memory, all these path metrics and that type of thing, right? So we're often implementing these, depending upon the processing rate, your architecture overall, that might be in an FPGA logic or software in a DSP processor chip or even a GPU, something like that, right? So, all right, so lots of words. Let's look at how this happens in practice, right? So here we have these different states, right? And we're going to have some receive bits. Now, here, there's a possibility, maybe even we call it a likelihood, that there's going to be some errors in these receive bits, right? So we're going to see that the Viterbi algorithm is still going to be able to ultimately produce the right results. Right? So, and again, there's a structure associated with this, right? So the generator polynomials are essentially the equations of those polynomials are encoded into this trellis diagram, producing these different transitions based upon the receive bit and the present state, right? So here we have we're again starting, assuming that we've been reset to 0, 0. I should make some notes here. So we're going to use the hard decisions, right? And we're going to assume that it's been flushed and reset to a state of 0, 0, right? So what do we do here, right? So we're starting here and we receive bits 0 and 1. Well, right off, we see that we should have gotten either parity bit 0, 0 or 1, 1, right? So right away we see that, oh man, that's an error, and we got it right at the beginning, right? We don't know whether we should have gotten a 1, 1, in which case that first bit is wrong, or maybe a 0, 0, in which case that second bit is wrong. But right from the get-go, we've got an error. Oh, man, how big a problem is that going to be? Well, let's see. So let's calculate our branch metric here at this state, right? So we know that this is a legal transition, right? So we got 0, 1. In this case, we would have expected to have gotten a 0, 0. So we calculate that distance or that metric there, right? And so what's the number of places that differs? It's 1, right? So there's a 1 there for a branch metric. It turns out that our path metric starts at 0, so that's our path metric also, right? So we add our branch metric of 1, and we add that to our path metric, which is 0, 0, and it's still 1. So, but this is also a potential state transition. So we look at that, and again, there's the number of positions that it differs is 1. So we write that down there, right? Now we step to the next time step where we received 1, 0. Right? So this is what the receiver is, its best guess at what it's receiving, right? And it receives 1, 0. So now if we're to get to this state, the only way would have been from this state right now, because, well, because we started in this state 0, 0, right? So again, let's compare that, and it differs in one location, right? So there's a branch metric of 1, but we add that to our previous path metric of 1 and end up with 2, right? So to get to this state from here, according to these input bits, these receive parity bits, we would have a path metric of 2, right? So let's calculate this one. We got 1, 0. We expected 1, 1. Again, that differs by a value of 1. We add that to our existing path metric, and we write down 2 there, right? Then we look at this one. Well, we've got 1, 0. We expected 1, 0. And so that branch metric is 0 plus to the existing path metric of 1 gives us a path metric of 1 there, right? And then finally, to get to this state, we've got a 0, 1, and that's a 1, 0, what we receive versus what we expected. That differs in 2 locations, right? So our branch metric is 2 plus our prior path metric of 1 gives us a path metric of 3, right? So we've gotten to this state right here, and these are our path metrics, right? So it looks like this guy's in the lead, but we're not done yet, right? So we know that there's lots of memory in the system. We already observed there's an error there. So let's keep going, right? So let's receive 1, 1. And we go through this. Now it starts to get a little bit more complicated, because to get to this state now, we see that there's 2 different legal transitions to get there, right? Before there was really only one, because of this kind of fact that we started at a reset trellis of 0, 0, right? But now we see that, well, we could end up in these states down here, right? And therefore, to get to this state, we might either transition this direction or you might transition this direction, right? So what we do is we calculate the branch metric for both of these, right? So here, this is 0, 0. We received 1, 1. So that branch metric is 2 plus 2 is 4, right? So, well, we're going to write that down over here, right? We're going to have a minimum operation, and we're going to write down this first branch metric. 2 plus 2 is 4, right? 2 from there, that branch metric, 2 from the prior path metric, right? Now, what's the other way we can get to this legally? Well, it would be from this state, right? And here we got we expected a 1, 1. And we got a 1, 1. So that branch metric is 0. Our prior path metric is 1, right? So we write down 1 plus 0. We're going to take the minimum of that. Well, what's the minimum of 4, comma 1? Well, it's 1, right? So we write down 1 there. This is our new path metric up to this time step for this state. Then we repeat it for these other states, right? So here, this transition, we expected 1, 1. We got 1, 1. So that branch metric is 0 plus 2. Rewrite that there. But we need to consider this other state, right? And transition, right? So we would expected to move from this state to that state would have been some parity bits of 0, 0. We got 1, 1. So that branch metric is 2. Our prior path metric is 1. So now we're doing a minimum of 2, comma 3. So let's save that 2. So we're going to write that down there. And here, just going to keep doing these examples. This transition is what? Maybe it's not written there. So we start off with the path metric of 2, and I think so it should be the same as this one, right? Because each step from one state to another it's always going to be the same, right? So if this is a 1, 0, so this is going to be a 1, 0 expected parity bit. So that varies by 1, right? So we have a 2 plus 1. And then the alternative is a 0, 1 compared to 1, 1. So that's a branch metric of 1 plus the prior path metric of 3. So it's minimum of 3 comma 4. So we write down 3 there. Note that in each of these steps, I've dashed one of these lines, one of these paths. And that's implying that that one is going to be discarded, right? And the solid one is what we call the survivor, right? So now this one is solid, and this one is so it's a survivor path, and this one is discarded, right? Because its path metric is larger. Finally, we look at this last one. We expected 0, 1 as parity bits. We got 1, 1. So there's a branch metric of 1, prior path of 2. Here we expected 1, 0 versus received 1, 1, branch metric of 1, prior path of 3. So minimum of 3 comma 4. We write that in and discard the path with the higher path metric. Right. So now we're just going to repeat that. So let's see, how much time do I have? So we're going to just repeat that. Let me kind of skip over a couple here, right? But because it's all just kind of stamping out the same, right? So let's look at this. We received 0, 0. We expected for this transition a 0, 0. So that matches with branch metric of 0, prior path of 2. Let's write down that 2 plus 0. We compare that from this legal transition, and that would produce, let's see, a 1, 1 versus 0, 0. That's a branch metric of 2, prior path of 2. So it's 2 comma 4, right? So we retain the 2, write down the 2, and draw this one in as a survivor path and discard this path, right? And so on, right? So generally our path metrics are going to continue to grow or at least stay the same, right? So because they're a summation. Now, let's receive this last one, right? And so we go through the same process and write down the results of these minimization operations. Again, basically choosing which path is the more likely one to transition, right? And it's all predicated upon a history, right? Of what the likeliest way of getting to a particular state is, right? And so now we go through at this time step, we've received 0, 0. We calculate all these things according to all these different state transitions. We put the two alternatives into this minimization function and choose the survivor paths, right? And we write down that accumulated path metric. Now, okay, so we're assuming that these are the last bits that received, the last set of parity bits that the receiver received, made its best estimate on, right? And so we look at which path was the smallest, right? Again, that means that it would have matched up the best at each stage. And so that one is 2, right? So this must be the best path or the maximum likelihood path through this trellis, right? And so I've just bold-faced these lines. I thickened them, right? But these would have been the solid lines, right? So if we look at here, there's a solid line there. That one's dashed, so we couldn't go that direction. We have to go this direction. So we're basically, retracing this at each step, right? So if we're at this one, okay, I know we're over here, right? But or maybe I'll just do it. from here, right? So if we're at this point, we can't go to this state because that path was discarded, right? This is the survivor path. And so we trace to there. And then we look, what are the legal paths here? Well, that's a legal path, but it was discarded, right? Because this path metric was too high. So we trace there. Again, we get to this point, that one was discarded, and that one is the survivor path. And then this one was discarded, but this was a survivor path. Survivor path, survivor path, right? And as we get back to the beginning, there were no multiple entrants into any given state because we assumed that we started here, right? So there's only some smaller set of legal transitions, right? So now we know how this thing evolved, right? So we can look at the bits, the parity bits that were associated with that, right? 0, 0, 0, 0, 0, 0. Oh, look, there's an error, right? So we received a 1, 0, but according to this decoding process, we should have gotten a 0, 0, right? So we're going to say that that parity bit was received in error. And then here, this one's 1, 1, this one's 1, 0, and this one's 1, 1. Okay, so there was an error there also, right? So we had 2 errors in all of this. Now, those are the parity bits, but let's look at the input bits or the message bits that would have produced those parity bits. Not the received ones, but the ones that the trellis expected, right? According to the legal structure associated with all these transitions, right? So at 0, 0, 0, 0, 0, 1, right? Okay, now we're going to reverse that because we really started here. And so it's a 1, 0, 0, 0, 0, 0, right? So that's what our code would be, right? So you can either trace back and pick off the input bits as we go through, and then once you get back to the beginning, then you can reorder them, or you can trace all the way back and then just read them off. Okay, typically you're tracing back and you're peeling off that as you go, and then you just reverse them, right? So it's so if we flush the system by ending our message with k minus 1 zeros, then we'll end up back at this state 0, 0, and we can start our trace back from there, right? So then our trace back from end to beginning, from end to beginning will be 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, right? So that's these parity bits here, 0, 0, 0, 0, 0, 0, 1, 1, and so on. Can I write that down again? Now every time I look at it, I feel like that's different. So there should have been, I'm not sure those things are right, but the algorithm is right. So now we look up these message bits while reordering, okay? Oh, I think what this is those are the memory locations, maybe. Yeah, those are memory locations that we're mapping to. So, so this is our maximally likelihood set of message bits. Excuse me. So note that we have errors in the first and 7th received bits. All right, again, we got an error in that first bit, or n equals 0, or yeah, I equals 0 or n equals 0. All right, and then the 7th one also, this one right there. Excuse me. Let me try water instead of coffee. Now, in that example, we had a finite number of parity bits that were received. We got to the end of that, and then we trace back. In some cases, we might have a continuous stream of data, right? We just might be transmitting message bits that get converted into parity bits, and we're just transmitting those, right? So, um, you know, we can have what we consider a continuous or almost infinite stream of data, right? If we waited until all that data is received before selecting the last survivor and then performing the traceback, then we would be faced with an excessive or almost infinite delay, right? And we'd have to wait around for excessively long time before we can figure out what our message is, right? That's bad. So what we can do is we can select a survivor based upon a factor related to the constraint length, right? So so there's some K here that is describing this constraint length, capital K, that describes the length of the generator polynomials and the number of states in the system and that type of thing, right? So we can use that to generate a metric, and maybe that's like a constraint length of 7 or something like. We'll call it. We kind of sometimes call it the same thing, but maybe we refer to it with a capital L or something. That we'll look out 7 time steps to, let's say this is 0, 1, 2, 3, 4, 5, 6. Okay, so maybe this keeps going, but at this point we do a trace back, and we can at least peel off these bits here and see that that's supposed to be a 1, 1 instead of a 0, 1, and therefore our message bit was 1. Then we can maybe process the next step and then trace back to this location and extract out another message bit, and then and receive 2 more receive bits, do all this calculation and trace back, and then recover this input bit, right? So that's how we can deal with this continuous stream of data. We're still going to select the survivor based upon a factor related to this constraint length, right? So when we do that, it's possible that our algorithm might make some errors, right? But the probability is vanishingly small, and the algorithm will eventually recover, right? And so that's the cool thing about it, right? So if we look at this, we maybe up to this point, we could have a path that looked like this, right? And both of these path metrics are the same. That's 2, that's 2, right? So which one is it? We don't really know yet. But if we had to make a decision, we would pick one randomly, right? We'd flip a coin and say, okay, well, let's choose this one, and we might write down then that our receive bits are 0, 0, and so on, right? 1, 0, right? But we still keep all these path metrics, and we keep iterating it, and so the algorithm will eventually correct itself, right? So recall that error control coding isn't perfect, right? In linear block codes, we looked at that depending upon this minimum distance metric that we ended up with, which is kind of related to the code rate and also the proper construction or the optimal construction of the code structure. Then we can detect a certain number of errors, and we can correct a certain number of errors. Typically, we can detect more than we can correct, right? But there's still a limit, and beyond that, we can't really reliably detect errors, right? So we might think that there's only one error, but there could be maybe half dozen errors, right? Or we might conclude that there were no errors, but maybe there were 2 errors that kind of canceled their effects out, right? Depending upon, again, the strength of that code. Maybe it takes 4 errors to fool the system into thinking that you had 0 errors, right? So again, there's no perfection here. It's a maximal likelihood detector, though, right? Decoder. So the Viterbi algorithm complexity, its storage and computational complexity is proportional to k minus 1. So that's practical for k is less than 10. So sequential decoding would be more practical for longer constraint lengths. We're not going to go into that. Most of your codes are, practical codes are simpler than this, and therefore we use the Viterbi algorithm decoder. So, we mentioned soft decisions earlier, soft decoding. So instead of calculating this Hamming distance from the bits, right, where each of those steps, we're looking at what the expected parity bits should be versus what the parity bits we receive, we can use, real numbers, let's say, that are from the voltages of the integrator sampler of the receiver, and then compare that to expected voltages at each step and state. And so now we're dealing with real numbers or floating point numbers instead of integer or fixed point numbers. Right. So, all right. So other codes. Well, first of all, bits are often permutated after coding according to a specific pattern to help deal with burst errors. So this is in addition to the interleaving that we have in convolutional coding, but we will sometimes use a pseudo-random sequence to now take a whole set of parity bits or code words, and now in a pseudo-random but deterministic way, move those around in time, right? So now you might have parity bits that are, instead of being adjacent to each other, are now separated from each other. So this splits and spreads information content away from a burst noise or interference, right? And obviously you've got to now reverse that process at the receiver to reorder everything. But if we've had some interference in a channel, then it's more likely to have only affected one of those parity bits, and maybe the other one is well separated in time, and so that can strengthen it. And so in typical systems like a 5G or Wi-Fi 6 type system or something like that, there'll be this permutation going on. You will also see that block codes and convolutional codes are cascaded together, right? So we'll use both of the linear block codes and a convolutional code so that we're kind of getting the best of both. Ultimately, we have some more sophisticated codes. There's turbo codes, low density parity check codes. So if you go into the 5G or Wi-Fi 6 type standards and look up what kind of error control coding are used there, then you will see LDPC codes, or like 4G use some turbo codes and stuff. There's some awkward patent issues there. So I think like the modern systems tend to move towards LDPC. There's some polar codes. All these are now really approaching the Shannon limit, allow you to get to that capacity equals B times log base 2 of 1 plus S over N. Right. So these type of codes here, these turbo and LDPCs, are iteratively solved using belief propagation and use this soft input and output. So similar to the Viterbi decoder, but there's some iterations going on there. So in summary, Convolutional codes address burst errors that can affect multiple symbols in a row. Linear block codes address statistically independent errors, such as arise from Gaussian noise. Convolutional codes are generated via state machine, implemented as a shift register. The code rate is 1 divided by the number of generators, and decoded using the Viterbi algorithm, which is implementing a maximum likelihood algorithm. Okay, so so when I do a assignment on this, when I release it, we might do something with a Hamming code that we talked about. This is a linear block code, and then we could also do something with a convolutional code. Note here we've got this trellis, and so here this trellis is going to be kind of defined and stuff. So that is describing the structure of that trellis. And then when you decode it, you're going to also provide it with this trellis type information. And so that's just another link to the same thing, right? So I'll provide all these links and I'll describe how to do it. And again, we're going to take our time in doing that. So we're getting towards the end of the semester and not too many more assignments to go. I see that most everyone is getting caught up, if not fully caught up. That's awesome. And so there'll be a couple more. I haven't figured out exactly how many more assignments. In the meantime, have a great little short break, and we'll see you next week, next Tuesday.
Thank you, Professor. Have a good break.
You too. Where is my, let's see, I've got to stop.